Hey there, calc folks, back here with another lecture in my study of the application of integration here, where we're going to see this integration process now playing out in what we think of as being an arc length calculation for the length along a function. All right. And we might consider finding the arc length along some function y equals f of x over values of x in some interval from a to b, right? And what we would be interested in would be something that I have very similar to what I have illustrated here, right? Here we have this function y equals f of x curving through space. And from x equal to a to x equal to b, there's this portion of the curve that we might be interested in finding the length of. And that's what we see going on here, right? We're interested in the arc length along y equals f of x from x equal to a to x equal to b, the length of this green section seen on my curve. And where this does come from is a formula, folks, right, given here by definition. The arc length of y equals f of x, right, a continuous function over values of x in this closed interval from a to b, right, is given by this calculation for the value we call L. And L here, L is just the integral from a to b for what is the integrand given by the square root of 1 plus the quantity f prime of x squared, all integrated with respect to x in the end, right? Here is our integrand, folks. And I will tell you, that integrand can really develop into some complex integration at times. And in a lot of cases, at least here with your fundamental rules that you have, that integrand you can't quite calculate for every single case you encounter. And in fact, there's going to be a lot of cases you're not going to be able to ever calculate that integrand for. What you will be able to do, though, is set it up, right, to think about it in theory, number one. And there are cases that the book does, there are tailored cases where if you are asked to find it, it really is a lot of algebraic tricks to go about simplifying that radical, right? Or presenting that radical into a format where something like U substitution might work. Or that radical eliminates itself so your integrand no longer involves the radical. And then one other technique we're going to learn in Chapter 8 is going to involve a little what we call trigonometric substitution that's going to allow us to integrate these things, folks. But for right now, we want to take note of there is this formula, and that in a few unique cases, with our current skills, we can evaluate this. One of those is the case we see down below here. I do work through an example with you in a case where this is can be considered and worked through from start to finish. And we might consider the length of f of x equals to 3 plus 4/3 x over values of x in this closed interval from 0 to 5. All right? Now, in this particular case, this is a line. This is a line in space starting at x equal to 0 and continuing up till x equal to 5. And we have a lot of geometric techniques to find lengths along lines, right? Distance formula being one of them. However, I do want to show you how to work through this, or how you would approach working through this with the arc length calculation seen above here in our definition. What we do take note of is for f of x equal to 3 plus 4/3 x, f prime of x is simply the constant 4/3. So if I square that, add 1 to it, and put it underneath a radical, right? This is the result I'm going to have. 4/3 squared becomes 16/9. Add 1 to that, that's going to be 9/9 plus 16/9, that's 25/9. And under the radical here, that becomes the square root of 25/9, which simplifies to 5/3. And that is going to be a constant value seen here in my integrand for this calculation. So if I want to find the length of this over this integral from 0 to 5, I'm just simply going to integrate 5/3 over that interval from 0 to 5. And that's what we do see in our calculation, right? The length of this curve, right, over this interval of x given by this closed interval from 0 to 5 is this value of L, which is the integral from 0 to 5 for 5/3 dx, where our antiderivative is just 5/3 x, where when we evaluate that from 0 to 5, we get 25/3 units in length, right? The length of that curve, or the length along that line, right, from x equal to 0 to x equal to 5, right, is 25/3 units in length. And we calculated that using the arc length calculation. You certainly could set it up a distance formula and double check that, and you would find that to be accurate. All right. Let's look at some proof. All right. As I did promise with these, we will see a bit of proof actually incorporate themselves into the work now. And now that we've seen some proof, and with all of our proofs so far, and what we're going to see continue in this integration process with respect to proof, is taking that subinterval of x, taking that interval of x from a to b and subdividing it into n subintervals. Where in this particular case, we're going to let delta x represent the length of the case subinterval, and we're going to let delta y be the change in y equal to f of x, be the change in the output over this kth subinterval. All right? This subdivision of the closed interval into n subintervals in turn is going to subdivide the length of y equals f of x, right, from x equal to a to x equal to b into n sublengths, right, where we can note the following illustration of those sublengths along with a measurement of delta x and delta y illustrated. Here we have our curve illustrated above, right, our generic curve, where we are interested in its length from this location where x equals a to this location where x equals b. And the way we're going to do that is we're going to subdivide from a to b into n subintervals. All right? This is going to in turn subdivide up our curve into sublengths. Right? Where for any given sublength, for the kth sublength, we'll maybe consider it to be this sublength here, we're going to have a measurement called delta x that describes the length of that interval. Right? And we're going to have a measurement for that length known as delta y, which describes the change in y, right? The change in the distance from here up to this location here, right? This vertical change over this kth subinterval of delta x, right? Whose length is delta x in size, right? This is what delta y is going to represent. And you can kind of see what we're going to do here. Hopefully you might have a little intuitive insight into this and note to actually approximate the length over this kth subinterval, we can use a little Pythagorean theorem and note that over the sublength L sub k can be approximated as the square root of delta x squared plus delta y squared. If we treat these as side measurements on a right triangle, the hypotenuse of that triangle would be approximately that length and size. So taking these side measurements squared, adding them together and putting them under a radical is going to give us the approximate length. Well, it's going to give us the length of the hypotenuse, which is approximately the length of this kth subinterval. All right? Which you can rewrite, folks. You can actually factor a delta x out from underneath the radical. You would have to factor it out of this term too, and when it comes out of the radical, it will unsquare itself, and you'll be left with the quantity 1 plus the quantity delta y over delta x squared underneath this radical. All right? So you can also consider writing L sub k this way, which is going to be a bit convenient for us in just a moment. All right? And here's an illustration of what we have going on, folks. With essentially, we are highlighting here, adding to our illustration above, that this length here, right, this hypotenuse length is going to be given by this this radical value of delta x squared plus delta y squared, which through a little bit of algebra can be rewritten into this statement seen here. All right? Now, to make an approximate for the total length, we add up the length seen in all k subintervals, and we can form this summation seen here. And once we have the summation seen there, we can make that approximate exact by applying a limit as n heads to infinity. Right? And our exact value becomes then the limit of this Riemann summation value, where this looks a lot like the definite integral, except f of x sub k has been replaced with this quantity seen here. All right. If we were to imply the definition of the definite integral from this, right, and note how it relates, right, we would be able to conclude using the definition of the definite integral that the limit of this Riemann sum would turn into this quantity here. And we have seen in that transformation the quantities of the deltas turning into the dy or the dx's, right, the d's statements. So delta y would become dy, delta x we understand becomes the dx. And this ratio inside here becomes dy dx, where for y equals f of x, right, dy dx is just the first derivative of f with respect to x. It's just f prime of x. So I can go into this statement seen up above here and replace this with f prime of x. And that's what we do. And what we end up with is the proof of the arc length calculation that we have seen above, folks. All right. We end up with proof for this calculation seen here in our definition. And note, it fits those proofs we saw in that set of notes that looked at the proofs from the earlier part of the chapter, right? At our earlier examples where I kind of held those off for a bit to kind of organize them all together there, just to kind of start to emphasize the meaning of the integration process and the meaning, the second meaning behind the application of integration, right? Yes, we can apply integration to calculate the arc length in given cases for functions over intervals of x, right? But we can also apply integration as this process, right, we see here in the proof to actually develop these integration calculations we perform in our calculations, right? And that is part of our study in this chapter. This is becoming familiar with how these formulas develop through some proof. Like I've said several times, this integration process can be applied in an infinite number of situations in theory. And that implies there's a lot of there's situations out there where that have yet to be discovered. And certainly if you understand how the process works, you may be somebody that can discover how to apply these ideas, right? So, I use that always as a little bit of motivation into learning this process, folks. It might be the thing that just allows you to, that you explore and that you discover, right, in future study. So, with that said, this has been a quick little video here over arc length. Like I said, there's a lot of examples where the calculation gets a bit complex. What you're going to see are some really fundamental situations to begin with here. They're going to get a little bit more complex when we get into some of the Chapter 8 and we learn a technique for calculating some integration that resemble these forms. And then in some cases we're going to take note of we're not always going to be able to integrate, and we're going to have to rely on some approximation techniques, some of which is built upon the proof that we just took note of, right? So, folks, another reason to also pay attention to some of this proof. All right. But with that said, I will end my video for tonight, and I'll see you in class. Take it easy.